Hey everybody. Today we're talking about strategies for testing infinite series for convergence and divergence. There's not any algorithm that you can just follow, no process that's guaranteed to work to get you from point A to point B. There's really an art to it. So this video really is just about some rules of thumb, some things to look for as you're trying to test convergence and divergence of new series. First of all, you really have to know the P series, sum of 1 over n to the P, and that it converges when P is greater than 1 and diverges for P less than or equal to 1. In particular, when P is 1, you have the harmonic series, 1 over n, that diverges. You've also got to know the geometric series, sum of a times r to the n, which converges when the absolute value of r is less than 1, and diverges otherwise. Always keep those in mind. Second of all, and the second very basic thing you've got to know, is the test for divergence. If the general term, an, doesn't go to 0, then the series diverges. You have to be a little careful with that, though, because if the general term does go to 0, the series could diverge, or it could converge. You have to do more work to figure it out. Let's do some examples and come up with some additional strategies as we go. Problem 1. Sum from n equals 0 to infinity, n plus 1, over the square root of n to the 4th plus 5. So this problem's illustrating an important idea. When you've got a sum of a fraction, where you've got polynomials on the top and bottom, or roots of polynomials on the top and bottom, or things that just look like polynomials, where you have n to non-integer powers, the long-term behavior of that general term is just going to be determined by the highest powers in the top and bottom. So here, n on the top, and square root of n to the 4th on the bottom. We expect this series to have the same kind of behavior as the harmonic series, sum of 1 over n, which is the simplified version of sum of n over the square root of n to the 4th. Now that harmonic series diverges, so we're expecting our series to diverge. Using this series, sum of 1 over n, as our comparison, we're going to do a limit comparison test. This is a good general technique. I look at the limit as n goes to infinity of the ratio of the terms. I know if this is a positive number, greater than 0, less than infinity, then the two series are going to have the same convergence behavior. In this case, they'll both diverge. So I'm going to do that division by multiplying by a reciprocal, and then I'm going to evaluate this limit by factoring out an n squared from the top and bottom. Those cancel, and then as n goes to infinity, the rest of that just gives me 1. So by the limit comparison test, these two series have the same behavior, and our series does diverge. Problem 2. Sum from n equals 1 to infinity, 3 to the n, over 7 to the n plus 1. I'm going to use the same principle as before. As n gets large, the 1 in the denominator isn't going to really make a difference, because 7 to the n is going to be enormous. So I expect this series to behave like the geometric series, sum of 3/7 to the n, the series I get when I just leave off that 1. Now, I'm going to do this with a direct comparison test. When I go from my series, 3 to the n over 7 to the n plus 1, to the one I want to compare to, 3/7 to the n, I've actually gotten bigger, because I've made the denominator smaller. Making the denominator smaller makes the fraction larger. So my series, which is positive, by the way, is less than or equal to a convergent series. So it has to converge by the comparison test. By the way, a limit comparison test using that same comparison series would definitely have worked here. And you should try that on your own. Problem 3. Sum n equals 1 to infinity, 3 to the n, n to the 5th over n factorial. This is a really good candidate for the ratio test. When you're looking at a series and seeing lots of products, quotients, and powers, and in particular when you're seeing factorials, you can expect that when you do a ratio test, you're going to get a lot of cancellation, and that you may be able to make some progress that way. So remember that the ratio test says limit n to infinity, absolute value an plus 1 over an. And if that gives you a number between 0 and 1, then including 0 but not including 1, then the series is going to converge. And if it gives you a number bigger than 1, then the series diverges. So you should try that on your own too. I'm not going to do that whole problem right here. Instead, let's look at this one. Sum n equals 0 to infinity, n over 2 plus n to the 3n. So when I see that exponent of 3 to the n on a function of n, I'm immediately wondering if the root test is going to help. When I take the nth root of that denominator, I'm going to get 2 plus n to the third power. So it's gotten a lot simpler. What about the numerator? Well, to evaluate that numerator as n goes to infinity, the nth root of n, you have to keep this fact in mind. As n goes to infinity, the nth root of n is 1. And also, you should just remember that the limit as n goes to infinity of the nth root of a constant is also going to be 1. Bearing those facts in mind, the root test is going to help you on problem 4. This is actually problem 5. It's labeled problem 4 here. Sum from n equals 2 to infinity, negative 1 to the n over the natural log of n. So when I see that negative 1 to the n, I'm recognizing I have an alternating series. And therefore, I'm immediately considering the alternating series test, which says that if this series has a general term that's going to 0 and it's decreasing, at least eventually, then the series is going to converge. So here an is going to be 1 over ln of n. By an, I mean what I have when I leave out the negative 1 to the n. And 1 over ln of n is going to decrease towards 0. Therefore, that series is going to converge. Problem 5. Sum n equals 2 to infinity, negative 1 to the n over ln of n. Again, alternating series. I can think about it in terms of the alternating series test. However, this time let's actually look at what happens as n goes to infinity. At first, I've got an infinity over infinity form. I use L'Hopital's rule and differentiate the top and bottom. 1 over 1 to the n is just n. And so as n goes to infinity, that goes to infinity. So by the test for divergence, this series is going to diverge. One more problem. Sum n equals 1 to infinity, ln of n over n squared. All right, so none of the strategies we've talked about so far are really going to help us here. It's not an alternating series. When we do a ratio, the natural logs aren't going to go away. Same thing with a root. And for me, there's not an obvious comparison here, although you might be able to find one if you look a little bit. This is a good candidate for the integral test, for 2 reasons. First of all, the integral test can sometimes be a good technique of last resort. It's very flexible, and it can help you when others don't seem to. Second of all, and perhaps more importantly, the general term, natural log of n over n squared, is a function that we are going to be able to integrate, in this case using integration by parts. So in order to apply the integral test, we need to make sure that the corresponding function, f of x equals ln of x over x squared, is eventually continuous, positive, and decreasing. Always got to check those 3 things for an integral test. Now, this is pretty clearly positive when x is bigger than 1. And it's also going to be continuous as long as we stay away from the asymptote at 0. The only thing we really need to check here is that it's decreasing. And as usual, we'll do that with the derivative. Differentiating ln x over x squared with the quotient rule, and then simplifying a little bit, I get 1 minus 2 ln x over x to the third. When x gets large, of course the denominator is positive. Ln x is going to be pretty large, and so 1 minus 2 ln x is going to be negative. So the function f of x is going to have a negative derivative eventually, and therefore be decreasing. The integral test is going to work here. All right, so let's actually apply it. Integral from 1 to infinity ln x over x squared dx. That's an improper integral, so I have to do it with a limit. Bear in mind, I don't care about the value of this limit. The value of this limit isn't going to tell me anything about the value of the series. All I'm interested in here is whether this improper integral, this limit, converges or not. If I get a finite number, then the series is going to converge, and if I don't get a finite number, the series is going to diverge. Okay, so I need an antiderivative, integration by parts. This is a good candidate for integration by parts because A, a u substitution isn't really going to do it, and B, integration by parts frequently helps me when I have a factor of natural log in my integrand. U equal ln x, dv is everything else, x to the negative second dx. differentiating u to get du is dx over x, and anti-differentiating v to get v equals negative x to the negative first, I plug into my formula for integration by parts. Integral of u dv equals uv minus the integral of v du. As usual, when I do integration by parts on a definite integral, I'm first going to get an antiderivative completely, and only then plug in my limits of integration. I'm left with one more integral to do here, integral of x to the negative second dx. That gives me negative x to the negative first. So overall, this is the limit I need to evaluate. So let's do it. Here I'm showing a very slightly simplified version. I've taken out the negative 1 and written the inside of that bracket with a common denominator. Plug in r, plug in 1, and remember that I only care about whether this converges or not, whether it's finite or not. I don't care about the actual value. So really, all I need to think about is the limit as r goes to infinity, ln r plus 1 over r. This is an infinity over infinity form. I need another L'Hopital's rule. 1 over r over 1 as r goes to infinity, that's just 0. So overall, our improper integral converges, and therefore so does our series.